And now we'll go to the next speaker, Mr. Lennart Petersen, who is an industrial PhD student from Aalborg University in Denmark. And he will talk about research and education at the Department of Energy Technology at Aalborg University. Please, Lennart Petersen.
Hello, good morning to all of you. And yeah, thanks for inviting me to this conference and giving me the opportunity to share our work on education and research. I will just quickly share my screen. Yeah, as Morten said, so I'm an industrial PhD, actually with the Aalborg University and Vestas. My name sounds pretty Danish, but I'm actually from northern Germany. But yeah, I've been living in Denmark for quite some years now. I'm presenting this partly on behalf of Florian Ioff, who is associate professor within the Department of Energy Technology. And I will speak a little bit about Aalborg University and our department, then talk a little bit about our education before we'll present a bit our Smart Energy Systems Lab. And finally, I will do some deep dive into my PhD research on off-grid hybrid power plants. Let's see how much time allows. So Aalborg University, we are a university in the northern part of Jutland. We have some organizational units located in Copenhagen and Esbjerg as well. We are covering quite a broad spectrum of research and education. We have almost 21,000 students, more than 800 PhD students. And maybe worth mentioning is that we are ranked #1 among the European universities in the field of engineering and the #8 worldwide. Then our Department of Energy Technology basically covers the entire spectrum from production, transmission, distribution, consumption, and also the control aspects of the energy system. We have a large focus on the technical aspects, but many times techno-economic studies are also indispensable for the optimal operation of energy and power systems and are part of the research as well. This slide shows a detailed overview of the department with various sections and research programs. My colleague Florian and me, we are anchored in the section of electric power systems and affiliated with the research programs Wind Power Systems and Intelligent Energy Networks, and Intelligent Energy Systems and Active Networks. And we are mainly focused on grid integration issues, control optimization, modeling, hybrid systems. I will explain a bit more about this. So and a special focus, of course, on wind here as well. We have quite a high number of PhD students and postdocs, up to 160, and approximately 450 students on the bachelor and master level. Talking a bit about the students, so we have a bachelor program where the students start to specialize in the 3rd year of their education. I highlighted here the specialization in electrical engineering. Also on the master level, then we have 3 different programs that focus on electrical engineering. One is primarily focused on device level, so power electronics and drives, whereas the other 2 are more on the system level. One of them is heavily focused on wind power systems. And problem-based learning is approach is a key element of the education, and I will explain it a bit on the following slide. So basically, a typical semester consists of 50% of coursework and 50% project work, which is in most cases group work. And the students find themselves in this cloud here where they have to solve a problem in a project, have access to many different resources. Then basically the problem funnel looks like this. So they start very broad, saving the world, but then they break down the problem further and further to a narrow project theme, project topic, which they will work on for the entire semester. These overall project themes are very well aligned with the coursework of the preceding semesters, but also of the current semesters. Project catalogs are given by the teachers, by the professors, but also to a large extent from companies. So we have a strong collaboration with many participants of the industry, among them also Folkecenter. So we are quite much in contact with Tony from Folkecenter regarding this. And yeah, so a typical project would look like this. This is an example impact of large penetration of PV and wind power into the low voltage network, where a heavy focus is laid on modeling of the grids, but also the assets. And then based on these models, you can derive methodologies and apply assessment studies and so on. More recent examples of student projects are listed here, where we cover both kilowatt scale, but also the megawatt scale. For example, there's quite an interest in virtual synchronous machines, which is beneficial for our grid operation. Then operation and control of hybrid systems for an isolated microgrid, power and energy management on the residential scale. On the megawatt scale, we have quite a large focus on grid code compliance, grid services, and energy services for market participation. And since a couple of years, most of the projects also include lab work quite heavily, and I will explain our lab in the following slide. So this is our so-called Smart Energy Systems Laboratory, which captures all the relevant domains, power systems and assets, control, but also the communication layer. The backbone of the lab is this real-time digital simulator by OpenRT, which enables us to represent the dynamics and characteristics of the power system itself, but also the assets. Then we have a possibility of connecting also physical components up to 50 kilowatt, enabling a so-called power hardware in the loop. So we have real battery units, PV emulators, and a flexible loads, a D-space system, which can represent small-scale wind turbine and some grid monitoring equipment. And then on top of that, we have different control layers, substation, supervisory control, aggregator control, which enables a controller hardware in the loop. And all elements are basically interfaced by an advanced communication infrastructure, which is administered by the Department of Electronic Systems. So here we are able to represent various communication networks, traffic patterns, and data collection mechanisms. It is worth mentioning that we are applying the so-called model-based design approach, which enables us to test components and systems up to a technology readiness level 6 or 7. And we are also included in the catalog of the European Joint Research Center for Smart Grid Systems. Then I will move from the education level more towards the research, and more specifically my own PhD project. So I started in 2017 to work with Vestas on a topic called proof of concept on next generation hybrid power plant control. I'm almost done with the work. I have to hand in my thesis actually in 2 months' time. So when we talk about hybrid power plants, what we see from the Vestas point of view is mainly this on-grid hybrid power plant where wind power can be supplemented by PV systems and battery systems and form a so-called grid integrated power plant unit. But then you can also spin it a bit further, and this is what I'm focusing on in my research. So you can focus on a so-called off-grid hybrid power plant, which is a consumer-directed standalone unit, where also diesel generation, for example, would play a role to basically keep the reliability of the system, and the demand is playing a big role here. And here we can distinguish between kilowatt systems and megawatt scale systems. So kilowatt scale systems would be for rural communities with total generation capacities in the, below 1 megawatt. But then megawatt scale systems could be, for example, remote energy intensive industry like rural coal mining facilities, pulp mills or cement kilns, remote military bases, for example, where we could reuse existing megawatt scale turbines. I've included more information about hybrid plants in this link here, so feel free to read if you want. Then I want to present a little bit my project workflow, which mainly consists of sizing, then moving towards control design and tuning, and control verification. And here I want to highlight why it is actually necessary to look at all these aspects to form a proof of concept. So there's a strong coupling between the different studies that I have listed here, and it requires a holistic viewpoint. So let's start with the first item, which is system configuration. Before we actually designing any control and operational strategies, we would need to look first into the system topology and the balance of plant. And then moreover, look into optimal sizing strategies. So what are the installed ratings of the distributed energy resources, which basically entails a techno-economic analysis to determine the system with the lowest cost of energy. The aim in this project was to design something that is modular and expandable, so you can adapt it to the demand levels, but also spin it further towards a megawatt scale plant. And basically, I came up with a benchmark system, a fictive benchmark system, which was designed according to a demand profile of a rural community in Africa, which consists of basically these units here. You can find more information on this link here. Then as soon as we have established a system, we need to design a stable voltage and frequency control system that should be reliable, but also configurable for various operating points. Because you might not want to run the diesel generators during all times due to cost optimization. So the control strategy has to be configurable. It requires, basically we do it via the model-based design approach. So it requires small signal models to assess the system stability, but also to tune the controllers. Then we can look into various system architectures. The one that I came up with is that you basically use diesel generators and battery units to so-called form the grid, so provide the voltage and frequency reference. And you just use standard controls by wind turbine and the PV system. And then you could use a central plant controller that is dispatching set points to the individual units. And this is just an example of kind of design architecture. Then as soon as we have this in place, we need to develop strategies to schedule and dispatch units according to generation and load forecast. And first of all, we need to focus on scheduling, like an hour ahead or intraday scheduling, which then determines how we actually do the runtime sharing of active and reactive power between the actual units, which is quite influenced by the dynamic fluctuations of wind and also PV for a cloudy site. And here on this slide, I just want to emphasize that such a work topic has a strong influence on, for example, the system configuration. So if we look into different probabilistic hour ahead forecast, so on the x-axis you have different confidence intervals for the forecast, and the higher the confidence interval, the more conservative is the forecast. That means it involves long operating hours of diesel gensets to ensure a certain amount of firm capacity. But then at the same time, you also reduce the number of power shortage that you would have due to a lack of wind or PV and low levels of battery state of charge. So there's a trade-off here, and depending on what kind of confidence intervals you choose, you have an impact on the cost, and that affects, of course, also the initially sized system that you came up with in the first place. Then what is a very important aspect already on the system configuration stage is to look into system security. And here we talk about the ability of the plant to handle short circuit faults, which requires a comprehensive analysis of all the possible faults that could happen in such an off-grid system. Most challenging cases actually when the synchronous generators are not in operation, because then you have only the inverter-based units contributing to the short circuit fault, which might be tricky. And I'm just highlighting for a specific fault in the system that with the genset in operation, you reach quite high current levels. This is shown in per unit levels, relevant for a protection device to actually trigger the fault. And if you disconnect the genset, you have very low short circuit current. So you might need to oversize for example, the battery inverter just to cope with these requirements, which also has an effect on the cost in the first place. Then another work stream is to look into large signal stability. So what happens actually if you lose one of the generation units in this plant? So it's the so-called N-1 criterion, which might require load and or generation shedding depending on the event. So in one obvious event is, or one obvious case of a blackout would be if you have the diesel gensets not operating, but then you lose the battery system, because then you don't have any unit that can form the grid. That also relates, of course, to the control strategy that you chose in the first place. And I just figured out that if you would modularize the battery unit, so instead of one big unit, you would install 3 smaller ones, you could reduce the severity of this event if one of the modules trips. And by designing an emergency control strategy, you can somehow cope with this event to keep the system stable. So it also affects, again, the initial system configuration stage. Finally, as a last stage, as a proof of concept, you need to address the interoperability of the control system, which I have done with the so-called control hardware in the loop approach. So by using the lab that I previously explained, having all the units modeled in a real-time simulator, and having the central controller placed in a real PLC platform, then you can verify both technical and economic performance criteria. So technical also relates to how to cope with communication losses and failures, which might require some modification of the control design in the first place. And regarding economic verification, I just want to highlight one case, and this is also the last slide of my presentation. So if we would, for example, look into a 24-hour operation, and we would compare a real-time hardware in the loop simulation, which includes all the dynamics of the system, compared to profiles which are just the hourly estimated ones that we have used for sizing the system. So then you can see, of course, the wind turbine has large fluctuations, also PV if it's a cloudy site. And that leads to a much higher cycling of the battery unit to compensate for these fluctuations. And the resulting energy throughput of the battery is much higher than you would have initially estimated. That again affects the cost, which you need to somehow take into account in the first place. So this is basically what I wanted to present. And to give a broad overview of that, you need to look into many different work streams in order to achieve a proof of concept of an off-grid system.
Thank you very much, Lennart. It has been really interesting, and also that you are down in kV scale, because that's actually what we are working with in this conference. I would like to say to all of you that we'll soon have a break, but before that, there are some questions coming in. Sven?
Yeah, thank you, Lennart, for a great presentation. If we go to the real world, I have had the pleasure of building such systems. One of the things that we really needed out there was inertia. And I couldn't see that as an issue that you at all had covered in your presentation. The way we built the inertia is by establishing a DC bus, so that everything basically goes on the DC bus. Do you have some comments on how to tackle enough inertia?
Yes, I mean, of course, this is part of the research as well. It's just in this short time I couldn't present all of that. Regarding inertia, I would say that I didn't see it as a big issue, due to the fact that you have in an off-grid system, especially in a case when you don't have any synchronous generation running, you basically have units that can operate or that can react to any system deviations very fast, especially if you have these grid forming inverter units. So it's a bit questionable if this topic of inertia is really that important in off-grid systems, since we don't have the same characteristics like in the large-scale system. So if you just have inverter-based systems that can all react very fast to any system deviations, there might not need to a large requirement for inertia.
Well, the thing that we experience with the small wind turbines is that they basically have no inertia, and when you have the inverter running back to back, you have nothing to help you from that side.
Yes, this is true. Like for units like a wind turbine or PV system, which basically doesn't have this capability of being fully dispatchable, it doesn't have a significant contribution. But then you can think of the battery system, which is fully dispatchable within the state of charge limit. So if you size the battery system in a certain way, you can actually achieve a lot by this unit, and because it can you can implement a control structure that reacts almost instantaneously to any system variation. That's what you also saw in the graph. So you have all these dynamic fluctuations of the battery that inherently compensates for wind and PV fluctuations.
Well, thank you very much, Lennart and Sven Enevoldsen. We'll soon have a short break in 20 minutes. That means we'll meet again about 10:30. The following breaks will be half an hour, but now you'll have time to stretch your legs, and we're having a long day, so wish you a good break. And then I'll ask you please to leave it, or don't close down. So don't exit, just leave it on. And if anybody wants to talk during the break, they can do that. Have a good break.
Before I go to my break, perhaps I can just comment on the inertia question. Where I have experienced that you need it the most is when it comes to unexpected or unplanned events like short circuits. I mean, if you want selectivity, when you have a short. The inverter-based systems without any inertia usually have their limitations. So you could end up with an island that has a complete blackout because of one small electrical fault. And of course there are inverters which are better at handling this and others are worse, but maybe that's a point which you didn't mention, Sven, but you had experience of also.
Well, it's a totally different grid systems that you experience when you really get out in the middle of nowhere. The place where we built the first hybrid system was in Patagonia, and most of the installations was with single wire. So you had one wire going into the house, and the return was earth. Yes, you had a lot of shorts and you had a lot of disturbances and whatnot. But the way we could handle some of the inertia was because we had the possibility of letting the synchronous generator on the diesel run free of the diesel. So we had some inertia in that one to assist, because we had no battery system there.
May I ask what size system that was?
We had 3 25 kilowatt turbines, the Viking turbines, and then we had a 110 kilowatt diesel. Average consumption over the day was about 30 kilowatt.
Yes. But then with the synchronous generator spinning all the time, I think you didn't have any selectivity problem, because that could deliver the short circuit current needed to trip any fuse, probably.
Correct.
Yeah, but if you don't have that rotating mass, if you just have inverters, that's my concern. And I mean, because of the advancement in batteries and power electronics, I see more of those systems. And I've been on these islands where it's gone completely dark because of a small electrical fault that would usually have tripped a small fuse, but then instead it trips the inverter, because usually in my experience the inverters have so good protection of themselves, so if there is a bad short, you know, it will not damage the inverter, it will just shut down. But that means you might not have any power.
Yeah, but the sexy thing about this system was that we have no inverters. It's directly asynchronous generators put onto the grid. So the only voltage control that we had came from the synchronous generator on the diesel genset.
Yes, I haven't done such a system myself, but I've read about them. Is this still operational, or what's the status?
Absolutely, you can find it on the Viking site. If you go into the website of Viking Wind, you can find the presentation of the Patagonia project.
Thanks, I didn't check that out. We'll try to do that.